Okay, students, this is the last video in subtopic 11.2, power generation and transmission. We've spent a lot of time talking about power generation. We actually haven't talked about transmission, so that's what this video is going to be about. I'm going to introduce the concept to you of a transformer, okay? A transformer is any device that changes AC voltage from one value to another, okay? So it can step it up or step it down. Okay, I'll talk about what that means in more detail later, okay? And the way it works is this, okay? We have an iron core. So this big piece of iron, that's one solid piece that's hollow in the middle, okay? And I have two different coils or two different copper wires wrapped around that core. One's over here and one's on the other side, okay? This iron confines, the reason why we use iron is because it has the property that it confines a magnetic field inside of it very nicely. So there's very little magnetic field outside of that core. Therefore, all the flux passes through the loops. We don't have to worry about flux being wasted outside, okay? Now, the first coil, which is called the primary coil, has N sub P turns. Remember how that variable N was very important in Faraday's law? We've basically been ignoring it. Well, now we're not going to ignore it. We're going to exploit that N to do something useful, okay? The second coil is called the secondary coil, and that's usually called N sub S turns, okay? The first coil is connected to an AC source, okay? Now, so we have an alternating current going through that wire back and forth, back and forth, back and forth, okay? All right, so we get a constant change in a magnetic field from this current, right? Because it's going up. In this diagram, it would be going up and down, up and down, up and down, okay? All right, now, because the iron has the property where it confines the B field, okay? That B field, that changing B field, enters the other set of coils on the other side, N sub S turns. So there's a flux in that set of coils, okay? So there's a change of flux in that secondary set of coils, so there's an induced EMF there. It's a very, very, very clever device. And what it can do is it can actually change the voltage from 110. Typically, it's used to change from 110 to 220 or back again, okay? Anyway, the induced, RMS voltage in the secondary set of coils is, of course, by Faraday's law, N sub S times d phi by dt, okay? And the RMS voltage in the primary set of coils is given by NP times d phi times dt. If I rearrange this, I end up with Vs over Vp equals Ns over Np, okay? So a very, very, very clever way to get a different potential, an induced potential, by utilizing the number of coils in Faraday's law, okay? All right, if you notice that if Ns is greater than Np, if the number of coils in the secondary coil is greater than primary, then we have that the secondary voltage is greater than the primary. That's called the step-up transformer. So it's quite amazing, right? You end up with a lower potential difference on one side, but on the other side, you stepped it up and you have a greater potential difference. It's pretty clever, okay? If the reverse is true, then it's called a step-down transformer, okay? So a step-up transformer, again, you would use it, say, if you had a device that you bought in, say, Great Britain or something that needs a 220 volt potential difference to work, and you're using it in North America, for example, you would use a step-up transformer taking 110 volts from your plug here, or in North America, and you would actually transform it to 220 so that you could then use your device. Step down is the other way. It's especially important because if I take, say, a hairdryer or something that I bought in the US at 110 and I go and use it in Great Britain and I just plug it into the wall, it's going to blow up because it's not designed to deal with that potential difference in that much energy. So I would need to use a step-down transformer, okay? A couple of things about transformers that are really important. They only work for AC voltage, or when that primary voltage is changing. It does not, they do not work for DC voltage. Well, why is that? Because direct current, you wouldn't have any B field, well, you wouldn't have a changing B field inside of that coil. It's the reversal of that current that causes that delta B, which causes a delta phi by Faraday's law to induce a voltage, okay? And the transformers don't change the frequency of voltage polarity oscillations. That's probably pretty obvious, right? So the frequency still stays the same, okay? Now, Since P equals VI, we can say that P sub P equals V sub P I sub P. So we have two different powers for the two different sets of coils. Okay. Now, assuming no power loss, I can rearrange it, and then I can then relate the ratio of the currents to the ratio of the coils, which is reversed on either side. Okay. In the IB data booklet, you're provided, I think, with this particular, or something to this effect. Okay. All right. So anyway, pretty cool, huh? And the way that they what engineers do is they actually coat these cores, and they have multiple layers insulated between them to reduce power loss and reducing the induced currents in the iron, because there are lots of induced currents that actually serve as almost like electrical friction to kind of slow things down. And this is what transformers look like. Here's a household one that you would use to convert like a hairdryer or microwave, whatever. On a bigger scale, you might see these around where you live, and they're typically behind chain link fences. These are gigantic transformers which are used to transport power over very, very long distances, which I'm going to talk about next. Okay. The circuit diagram symbol for a transformer is something like this, which is kind of cute, actually. Okay. All right. So go ahead and try this example, this IB sort of style example. Okay. And this term ideal transformer just means a transformer for which we can use those equations that I just introduced to you. Okay. So try this one. So we have a step-down transformer from 220 to 4.5, so it can charge a mobile phone. Okay. Transformers are used in all kinds of devices, all right? All kinds of, when you charge your phone, you charge your computer, whatever, there's lots of stepping up and stepping down that has to be done in order for your device to work correctly, okay? Anyway, if the primary has 500 turns, how many does the secondary have? Well, you just rearrange that equation I gave you, and you get that it's 10 turns, okay? If the charger delivers about a half an amp to the phone, how much power does it deliver? Well, P equals IV. Right, that's easy. How much current flows into the transformer from the mains? Okay, that's I sub P. We would use this version of the equation, 9.1 times 10 to the minus 3 amps. If the phone is unplugged from the charger, but the charger is left plugged in, how much current flows in the charger now? Well, of course, 0, because the charger's leads connect to a circuit. Without the phone, there's no circuit, so you don't have to worry about wasting electricity when you leave your charger plugged in. Okay. That's just simple physics. Okay, now, transformers are crucial for electrical power transmission. Let me explain how this works. This is a pretty cute diagram. Here's your power plant. Your power plant is the place that has those gigantic rotating coils inside of huge magnets, okay? Now, the potential difference in those wires as when that power comes out of that power plant might have, for example, 12 kilovolts, okay? In order to transport it, what we want to do is we actually want to step up that voltage as high as possible. And that's why these transmission lines are called high voltage transmission lines. Okay, so they travel long distances. I'll explain why that is. But then when it gets to a neighborhood, we want to step that voltage back down. Okay, and then it steps it down again in order to go into people's houses. If you had a potential difference of 240 kilovolts when you plug something into your house, all the stuff in your house would blow up. It would be pretty horrible and scary. Okay, so again, in your house, depending on where you live, the wall outlets give you either 110 or 220. Okay, it's just a source of potential difference. An average city has several megawatts of power demand at any given time, meaning every second several million joules of energy. Okay, the power station creates the original delta V, or potential difference, and the current flows through cables up and over towers, normally through a giant circuit. And the transformers step it up or step it down, the PD I'm talking about. Okay. All right. Now, the potential difference at the power plant is greater than 110 or 220. Okay, it's greater. Why? Well, because of friction within the cables, and I'm talking electrical resistance, right? Friction within the cables. Some power is always lost. Now, because P is I squared R, okay, where R is the total resistance of those cables, and remember resistivity and all that, we talked about the cross-sectional area of the wires and the length of the cable, that's a factor also, okay, but that resistance is very, very hard to change, okay, but the current is very easy to change, and not only that, current has a greater effect on the power loss because that variable is squared in this equation, okay. So somewhere between the station and your house, there's a reduction in the current to reduce the power loss, right? Okay. Now, since P equals VI, if I reduce the current, I increase the voltage, right? Okay. And so what that does is, because P equals I squared R, by reducing the current when I'm transporting it, that power that's lost actually goes down, which is what we want, right? So transformers step up the voltage after leaving the station, but step it down again before entering your house. So, you know those high voltage transmission lines that everyone says, oh my gosh, don't touch, they're super dangerous. Sometimes you can hear them buzzing above you. They do have high voltage, but they have a relatively low current, relatively low amperage in them compared to what they were before, okay? All right. Okay. So try example 7, power station generating electricity. Okay, these are very typical numbers for an average situation. Okay, how much current will flow through the cables that take the electricity away from the power station to town? Okay, P equals IV. This is what, 5,000 amps. How much power is lost in the cables? Okay, P equals I squared R. That's 200 megawatts. Okay, the total power that's delivered is lost is going to be the ratio of 200 megawatts, which was given in the problem. Sorry, 500 megawatts given in the problem. 200 divided by that times 100 is 40%. How much power delivered to the town? Now, we always assume that the transformers are 100% efficient. That's 300 megawatts. So therefore, how much total current flows through the town? 1.36 mega amps. Okay, so a very, very typical application of this kind of thing. So it's important for you to both qualitatively and quantitatively understand how transformers aid in the transmission of power from a power station to your house. Okay, all right, try this one. Okay, so again, how much current flows in the power station? P equals VI. What makes these problems maybe possibly tricky is that you have two different voltages to work with. So when you're using Ohm's law, P equals VI and all that, you have to be very careful. You have to know which one you're talking about. Okay, percentage loss of power in the cables. Okay, that's I squared R. That's 69 megawatts. The percentage loss is 69 over 500. It's only 14%. That's not bad. Okay, if the electricity were transmitted at a lower voltage, what would the power loss be? Well, it would be a lot more, right? It'd be 32%, okay? So you can see the effect, if you look at these calculations, you can see the effect of transmitting at a lower voltage as opposed to a higher voltage, okay? Okay, so what about living and working near transmission lines? Okay, there's a lot of controversy. About this. Some people think that if there's big power lines going through your neighborhood, you know, there's more of an incidence of cancer, leukemia, and all this kind of stuff. Okay, I'm going to talk a little bit about that, and I'm just going to present to you sort of the facts from a physical point of view, and then you can kind of draw your own conclusion. Okay, the big question is it risky? Okay, all right. Well, it can be risky. So electrical power lines that are not insulated along their entire length can be extremely dangerous if they come down from the tower, because if you touch them, you can get electrocuted, okay? Number two, you know that a current carrying wire carries a B field, right? There is statistical evidence that suggests, but does not prove, there are regions near power lines where children are diagnosed with leukemia, which is cancer of the blood, more often. And these are called leukemia clusters. The reasons are not understood, okay? So there's a suggestion, but it's not a direct link that has been proven, okay? Now here's the physics. So we have alternating currents flowing through, oscillating 50 to 60 times per second. These currents induce low-frequency electromagnetic fields, okay? And it's thought that these electromagnetic fields could induce currents inside any conductor nearby. In fact, that does happen. The question is, when you consider the human body as a conductor, is it possible to ionize atoms inside the human tissue? Because after all, that's what causes cancer, okay? All right? We will study later about quanta and photon packets, but I'll tell you now that electromagnetic radiation travels in very discrete amounts of energy. And that discrete amount of energy is proportional to the frequency, E equals hf, where h is Planck's constant, okay? All right? It turns out that these quanta don't have enough energy to cause ionization. It's been proven that you need more energy than that to actually strip an electron off of an atom inside of a human cell tissue, okay? Experimental evidence currently, at this point in time, there is no direct solid evidence that such low frequency electromagnetic radiation has any link to health problems, okay? So that's kind of the physics, all right? Okay, if there are risks, they're probably dependent on three factors. Number one, the current density, right? How much current you have going through those wires. Number two, the frequency of alternating current. And number three, which is maybe the most important one, and that is the length of exposure. Okay, all right. So you want to think about, this is a really interesting topic, which brings up the idea of correlation and cause. And if you think about that, like in your TOK capacity, right? There's a lot of false stuff out there about this topic, right? You get online and you talk about, there's all this dramatic stuff about, first of all, there's lots of bad graphs, right? If you look at these graphs, like most people, what is that? Odds ratio to magnetic flux density. You know, look at this, like the invisible killer, daily sources of EMF. Well, of course, it's not the EMF that kills you, right? It's the radiation that is, or the effects of your cells from the magnetic field, which in turn affects moving charge and currents and things like this, right? We've studied all that. So you want to think very carefully about correlation and cause, and we'll talk in class a little bit about, we'll kind of maybe come to our own conclusions about whether or not there really is a correlation between these things. Are they correlated really? Does one cause the other? Because those are two very, very different things.